Previously, we've seen that we can make an approximate simulation of the motion of objects using graph paper. Let's look at an example of this. Suppose I launch a projectile at 50 meters per second initial speed at an inclination of 53 degrees above the horizontal. In this simulation, we're going to be graphing y, measured in meters, the height of the projectile in meters, versus the distance it's traveled along the ground, x, measured in meters as well. Now, this object is only subject to one force, and that force acts straight down, which is going to cause it to have an acceleration g 10 meters per second, or 10 meters per second squared downward. What this means is that the y component of its velocity is going to change over time, but the x component, since there's no force in the x direction, we're ignoring wind resistance, there's no force in the x direction, the x component will stay the same. We chose this 53-degree angle for a reason, for simplicity. I happen to know that 53 degrees is one of the angles in a 3, 4, 5 triangle. So if I move over 3 and up 4 squares, representing 30 meters per second across and 40 meters per second up, I'll have a length of 50 meters per second for this velocity vector. Now let's see what happens after 1 second. We said that the horizontal component of the velocity is still going to be 30 meters per second, but the vertical is going to drop from 40 down to 30. So we're coming up 3 squares and over 3 squares, giving us this for our next velocity. What happens in the following second? There's still no change in x, so we come over 3 squares to represent 30 meters per second of horizontal speed, but whereas we went up 4, then up 3, now we're going to only move up 2 squares. Here's our new velocity. Extending this pattern, we continue to move over 3, but now we only move up 1. We've lost another 10 meters per second of speed due to the influence of gravity over the past second. Another second goes by, and now we only have 10 meters per second of vertical speed left, and we lose that much every second. So we're going to move over 3, but not up at all. This procedure continues, but now we have no vertical speed, and we're just going to keep losing 10 meters per second, meaning our vertical speed will become negative. So now we move over 3 still, but down 1 square, representing negative 10 meters per second of speed. We still move over 3 as always, but now down 2. Over 3 and down 3. Over 3 and down 4, and our particle has hit the ground. Each of these positions represents the position of the particle 1 second later than the position before it. We know this is an approximation because this motion is always curved, but we've pretended it was a straight line between segments. We'll talk more about that approximation later. Remember, each interval here represented 1 second, and we're traveling 30 meters horizontally every second. So let's put in some dashes on our x-axis. So we've projected a range of 270 meters for this particle launched at 50 meters per second with an angle of 53 above the horizontal. Adding coordinates to our y-axis, we've predicted a height of 100 meters at the apex of the motion. Finally, let's add a t-chart to keep track of time, x and y, and horizontal and vertical velocities. Horizontal velocity never changes, but vertical velocity drops by 10 every time. X is increased by 30 because the velocity is always 30 horizontally. At the end of the 8th second, we reach 270, but the pattern of our y points is a little bit more complex. And at the end of the 8th second, 9 seconds, we reach the ground again at 270. Notice this motion is symmetric, and think about why that might be the case. And it's a particular curved mathematical shape. Have you seen that shape before? What is it? Ours is approximated with straight line segments, but the actual motion will be curved everywhere. Next, let's graph these velocity functions as a function of time and see how they look. So we see Vx is a horizontal function and Vy is a diagonal line here with a particular slope. What does that slope represent? It's the change in Vy divided by how much time that change took. I see 10 minus 20 is negative 10, over 3 minus 2 is 1. Negative 10 over 1 is negative 10. What are the units of this slope if my vertical axis is meters per second and my horizontal axis is seconds? In the next video, we'll see how to replicate this kind of simulation using a spreadsheet. Thanks for watching.